All right, so we're going to continue with our section on limits. We've already discussed the basic idea of what a limit is. Now we want to talk more about how to compute them, especially in cases where it might not be obvious how to do it just from a graph. Or maybe we don't have a graph. So here is the good news. As long as we're not doing some kind of illegal mathematical operation, right? We're not allowed to divide by zero. We're not allowed to take square roots of negatives. But if it feels like we're just doing normal math, then you can trust your intuition about limits. Right? So here's an example. If I just gave you this, what's the limit as x approaches 5 of x squared minus x? Well, you could say to yourself, well, I've got this function, f of x is x squared minus x. What if I just plug in 5? I get 25 minus 5, which is 20. So f of 5 is 20. So if I'm near 5, I should be near 20. So the answer here is 20. We basically just plug in. We plugged in, and that didn't require any illegal math. That's the answer. If it just feels like you're getting an answer doing nice, simple things, you're probably fine. Right? Here's another example. So think about this. This one's a little more abstract. So I have this function f of x, and the limit as x approaches 0 of f of x is 4. And here's g, the limit as x approaches 0 of g of x is 7. And let's notice, in both cases, we're talking about what happens when x is close to 0. So now I'm asking, what's the limit, again as x is close to 0, of f of x plus g of x plus 2? So stop and ask yourself, what does this mean, and what do I think the answer is? So we know if x is close to 0, f of x is very close to 4. We know if x is close to 0, g of x is very close to 7. And this is simply the number 2. So we're dealing with something that is a number close to 4 plus a number close to 7 plus a number close to 2. And remember, close means very, very close. So we're going to get something close to 13, and that's our limit. Basically, we just took 4 plus 7 plus 2. If it feels like you're just plugging in and doing very obvious things, and you're not doing anything weird like dividing by 0, then trust your intuition. Now, that's the good news. The bad news is usually when we actually care about limits in the context of doing calculus, it's because we are doing something weird. Dividing by 0 is a very common phenomenon in the sorts of problems we want to think about. So we are going to have to learn some tricks for what happens when we can't just plug in. And I'm just going to warn you, you're going to see a lot of problems where if you plug in, there's a 0 in the denominator. So I'll just pause. If you're dividing by 0, pause and think about a method for getting the limits. We can't use our intuition. And technically speaking, we're dealing with a function that's undefined. But there are some well-known techniques that will help you figure out the limits. So here's the first one. Some people call this factoring and canceling. And this will be the most common technique. There's some other limits we'll just memorize, and there are some techniques in this section that are like this, but just trickier. So the idea is, if we're getting 0 in the top and 0 in the bottom when we plug in, maybe we can do some clever algebra to somehow get those zeros to disappear. So let's look at an example. And this is the example we did at the beginning of this section. We already know that that limit's supposed to be, whoa, I didn't want to paste, I wanted to copy. So just watch this. So we've already done some work here. We know this answer is supposed to be 5 because of numerical stuff. But here's a way you can do this analytically. So we'll just observe, right? Observation. plugging in gives 0 over 0. We're dealing with a case where the function is undefined at 2, but there's probably a limit we can think about when x is close to 2. If you're getting 0 over 0, you really want to start looking for, can algebra get me out of this? So be on the lookout for anything you see that can simplify or that can factor. And hopefully you're noticing that this trinomial up top factors. It factors as x minus 2 times x plus 3. And now we can see that we have the factor of x minus 2 in the numerator and x minus 2 in the denominator. So after cancellation, we have the limit as x approaches 2 of x plus 3. Now remember, when limits feel easy and we're doing intuitive things, we can trust our intuition. If I just handed you this problem, you could say, oh, well, x is close to 2, and I'm taking something close to 2 plus 3. That answer is close to 5, so my limit is 5. We factored, and the thing that was giving us 0 over 0, we were able to cancel it away. And what I will tell you, right, keep this in mind, for what we'll call 0 over 0 limits. Usually, right, not always, but usually you can cancel something. Use this knowledge to guide your algebra. In this example, I'm getting 0 on the top, 0 on the bottom. With my experience, I realize, oh, it's 0 over 0. I'm probably going to be able to cancel something. Now, maybe you can't factor this right away, but you could say to yourself, well, I feel like this x minus 2 in the bottom is supposed to cancel away. Well, it can only cancel away if I have x minus 2 in the top. So knowing that I'm supposed to have x minus 2 in the top makes this factoring much faster in case you couldn't do it right away or you didn't notice it right away. Keep in mind that you're supposed to be able to cancel things. That'll make it more obvious how to simplify or how to factor. Okay, so with that in mind, try these two examples. I will tell you that this one you already did. We did it numerically, we did it with a graph. So see if you get the same answer. But both of these, try to mimic what I did in that previous section. All right, so for this first one, what did you get? And let's go through this. Now, I just want you to know, if I am doing a limit problem, then at every relevant stage, I write the limit part. A lot of students leave that out. Sometimes that really throws them off towards the end. Maybe not in a problem like this, but I've seen it happen. Failing to write the limit confuses people as to what they're doing in the first place. Well, we have 0 on the top, 0 on the bottom if we plug in. So this x minus 4 is probably going to cancel with something. So I should have an x minus 4 here. And maybe you remember your difference of perfect squares factorization. So I have x minus 4 in the top, x minus 4 in the bottom. After I cancel, this is the limit, keep writing it, of x plus 4. And now this is one of these problems where I can trust my intuition. Oh, x is close to 4, and I'm taking x plus 4. So a number close to 4 plus 4, I get 8, and that limit is 8. Once we're writing our final answer, we don't need to write the limit notation. And that's what we got before. All right, this one's a little bit trickier. What did you get? Okay, so let's just double check. If we plug in, we get negative 4 plus 4 in the top, and we get 12 plus negative 2 minus 10 in the bottom. That's 0 over 0. So we are looking to factor and cancel. Now here it might not be so obvious. Let's look at the numerator first. In the numerator, all we can do is factor out a 2. But we can use this as a guide. We can now say, oh, this x plus 2, something is supposed to cancel. And in the numerator, all I have is 2, which is just a number. That's not going to ever give us 0. Right? This algebraic thing is probably what's going to cancel. So maybe one of my factors in the bottom is x plus 2. Well, if I'm getting 3x squared in the front from x, I probably had x times 3x. And if I'm getting negative 10 here, I probably had 2 times negative 5. And it's not a bad idea to check that middle term. My outers give me negative 5x, my inners give me 6x, so that gives me x. So this is the correct factorization. And I found it a lot faster because I knew I would probably be canceling something. So those two factors of x plus 2 cancel. Remember, you can only, in a fraction, you can only cancel entire factors. Right? Please don't be the person who says like, oh, I see an x and I see an x and I cross them out. Canceling does not mean you see something twice and you erase both of them. You really need to understand what operation are we doing. The operation here is that I have taken my entire numerator and I divided it by x plus 2. And I took my entire denominator and divided it by x plus 2. That's why we're allowed to cancel those. They have to be entire factors, not just isolated things that we have written down. But after we cancel, we're left with just 2 in the numerator and 3x minus 5 in the denominator. So now, well, let's trust our intuition. Our numerator is just the number 2. And if x is close to negative 2, then this is close to negative 6 minus 5. We have a number like negative 11, and our answer is negative 2/11. And I just want to point out, if you saw this number negative 2/11 in decimal approximation based upon a graph or a table, I'm not sure if you would recognize it, right? I'm not even sure if I would recognize it. I might just say like, oh yeah, I have this decimal and it's around negative 0.19. Huh. Doing the algebra is sometimes the only way for us to say very clearly, here is exactly what that limit is. All right, we will pause again, and more will come in future videos.